Okay, so picking up where we left off, this was the CD. Then we're just adding ACD over here, A and CD, and then B and CD. So now what's going to have to happen next is from just inspection, we're going to have to delete these lines because what I thought was going to work is not going to work. But it's okay. You kind of have some mini bus lines over here. This is the way. We're still doing all right. Just everything is all good. You might want to move these up a little. Move this line up so it looks nice. See how we're still pulling from A. So you can move all these up a little if you want. Okay. So now we need the OR equivalent of NAND gates, or the two items you want to OR get split into two NANDs that get combined into a third NAND. So hopefully you remember this equivalent of an OR. We're converting these ORs into 3 NAND gates per the equivalent. Remember, to earn maximum points, you have to physically circuit the cutoff valve with NAND gates. That's a whole part of this project. However, if you want to circuit using AOI logic, you will be sacrificing part of your project points. So it is up to you, whatever you want to physically circuit. But to make sure you physically circuit correct, in the NAND world, we might as well. You want to multiply them on using 74LS00s, which are NANDs. So we need 3 in a row. So what we're doing is stacking. Let's do this one first. Let's stack here. Cancel. Okay. This one is ABC. So I believe this one gets split. This is ABD. This gets split. And then they combine here. Okay. So that is ABD or ABC. And we need to do the OR part over here, BCD or ACD. Here's our ACD. Here's our BCD. So we need to place, let's do 3 more NANDs. Let's use a new chip. 1, 2, 3. Let's put the 4, close. Let's just use the 5th chip for this. So this one gets split here. This one gets split here. And when you split it, they combine to the 3rd NAND. Right here. So here we have ABC or ABD. Here we have ACD or BCD. We need to combine these again. Let you a 3rd chip. Yes, we are using a lot of NAND chips, but that's the whole point of this project. Let's use a new chip. This is the 6th chip. That's why it's U6 here. Use the C gate. Let's see how this works. Close. This one gets split here. If I'm reading the diagram right, this one gets split here. And they combine here. Combines here. Then the final output is a green probe. which is an indicator here. Probe, let's use green since we're going to use a green LED on our proto board. Close, this is the cutoff, green's the cutoff using NAND. Let's run this. It should only light green when 3 are on, so all zeros. First one, we're just counting in binary, we're doing the truth table. CD should turn on, that is correct. 0, 0, 1, 1, 1 should turn on, that's correct. Doing all scenarios in binary. You can see the switches flicker. That's on, 1, 0, 1, 1. 1, 1, 0, 0 is off. 1, 1, 0, 1 is on, right there. 1, 1, 1, 0 is on when all 4 are on. Okay, NAND logic. Hopefully you got the, oops, I should probably turn this on. Hopefully you got the indicator green probe to turn on when any 3 of the 4 are flickered on, or all 4. Okay, let's turn off all the switches. Let's go to the NAND PowerPoint available on Canvas. What happens is if you have 2 inverters in a row, you can delete them. NAND implementation. Identify and eliminate any double inversions. A double inversion is 2 in a row of a wire getting split into 2, inverted, and that same wire getting split into 2, inverted, because a double negative would just lead to a positive. So here's your PowerPoint example. It would simplify to that. You can eliminate any 2 in a row, and then this example circuit would simplify to that. That's why it's kind of helpful to do this on paper first, where you diagram it in your engineering notebook using AOI logic first, which is here. And then you convert everything to all NAND logic, and then you find the double inversions. Well, since we didn't do that, let's find our double inversions here. So maybe you want to rearrange this to, let me turn this off, to make it look nice and neat. Okay, so here's the roadmap. We're just looking for wires that are double inversions. We want 2 inverters in a row, 2 NANDs, 2 of these guys in a row where the wire gets split, and the wire gets split with an output in a row, because that is basically 2 inverters in a row. So where do those happen? Here's a split here. Let's see, that output goes here and here. That's not a double inverter. So we kind of don't have a double inverter here. 2 separate into 1 to split, not a double inverter. Let's look at this one. This wire gets split here. That output gets split again to here. Here is a case of a double inversion, this one and this one. So since it's a double inverter, we get to delete it. Here's another case. Delete, delete. Split to 1, split to 1, that is a double inverter. So is that one. So basically what you get to do now is simplify the circuits. Instead of having those 2 inverters in a row, we're saving logic chips and logic gates. So now, hopefully this NAND circuit looks a little more simplified. We got to check our work. When they're all 0, it is not on. We'll just run through the binary combinations, A, B, C, D. All zeros, 0, 0, 0, 1, 0, 0, 1, 0, still off. 0, 0, 1, 1, still off, because at least 3 need to be on for the green indicator to turn on. 0, 1, 0, 0, still off. Binary high 5, 0, 1, 0, 1, still off. 0, 1, 1, 0, still off. How about 0, 1, 1, 1? Should turn on. Removing the double inverters of the NAND equivalent still makes the circuit work. So now 1, 0, 0, 0 still off. Running through the binary truth table. 1, 0, 0, 1 still off. 1, 0, 1, 0 still off. What about 1, 0, 1, 1? Turns on. 1, 1, 0, 0 still off. 1, 1, 0, 1 on. 1, 1, 1, 0 on. All ones, it is on. So this is actually the simplified NAND circuit for the cutoff, the green probe. We remove these double inverters because 2 inverters in a row is the same as just connecting the wire to where you want it to go. We are all using one style of chip, the NAND chip 74LS00. And so now we need to look at the fault indicator. This is the red probe or the red LED when you start protoboarding. Let's make sure our truth table is accurate. And when your truth table is accurate, hopefully that stays there, you got to make sure your K-map is accurate. I don't know why those things keep falling, but that's all right. So basically, everything is 1 except for this spot and this spot on the K-map. Because the fault will always output 1 unless all 4 sensors are 0 or all 4 sensors are 1. So here's the simplified expression. The one there. Okay. So how did we come about that simplified expression? Remember, in K-mapping, your goal is to make groups of 4. Your goal is to make groups of 4 by circling each number 1 at least one time. So hopefully I could color code this. There are 4 groups of 4 you can possibly do. The green is the row A, B naught. That's that. The far right vertical row is in yellow. That is C, D naught. Okay, here's where it gets tricky. The magenta is going to be this square group of 4. That is A naught D. That's that group of 4. And then the blue, or let me do the magenta, that's AD. Oh, whoops. AD naught. Sorry about that. And then the magenta, or the sky blue group would be this square group of 4, which is B, C naught. There it is. So that is your logic expression. First thing you should do is draw your AOI logic for the faults. So you draw your bus lines. And then you just do this circuit as you go. So let's do C, D naught. Pulling from D, you might need a triangle inverter. And the C, that is an AND. Remember, that's an inverter. So we're good with that. A, B naught. B, we're going to invert this guy. And it goes with an AND with the A. A naught D. A. No. Yes. A. Invert A with D. That's that. And then B, C naught. B positive. C inverter. Now these triangles are inverters. B, C naught. I kind of went out of order. Hopefully you could follow where the inverters go. Then we need to OR all these. You need to OR all these ANDs. So this gets pulled into